Now, there are many variants of TCP congestion control. Started with TCP Tahoe by Van Jacobson in '88, as we just mentioned. And then 2 years later, Van Jacobson himself modified Tahoe by incorporating smarter ways to deal with the slow start and smarter way to differentiate different kind of congestion signals, the details which do not concern us in this lecture. And he named that after another city, TCP Reno, in 1990. Then there was a plethora of different TCP variants, including TCP Vegas in 1995, which uses delay rather than loss-based congestion signal. This is delay instead of loss. And then in the late 90s and early 2000, another surge of different TCP proposals were presented, including one called FAST in 2002. And this one uses primarily delay as the basis, but with stabilization using control theory to make sure that convergence can be achieved in this iterative procedure of going up and down in the bandwidth demand. And several years later, another TCP variant called Cubic was developed, and a year later it got into the standardization of Linux kernel. So at this point, for example, a lot of the Windows TCP are still based on Reno, but for Linux-based TCP, the default is Cubic, which uses a combination of delay and loss as the congestion signal. Okay, so last time we checked, about 40% of the server-generated internet traffic uses Cubic, for example. So as you can see that there are two main families of congestion signals. One is loss, the other is delay. So for loss-based congestion inference, what happens is the following. Let's say, take a small example. Over time units measured by round-trip times. Let's assume round-trip time is fixed for now. Actually, it does vary and can vary quite a lot if there's a lot of congestion variations. Let's say we start with a congestion window being 5 packets, okay? And after one round-trip time, okay, here's the source, here's the destination, separated by the distance, and this again is the time axis vertically. So 5 packets got sent. Let's say they all properly are received by the destination, and then 5 acknowledgements are sent. So this time is one round-trip time, RTT. Okay? And therefore, the sliding window is slided 5 times. Plus, there is an increase. So slide plus increase. Now, how much do you increase? For each acknowledgement you received, increase by 1 over CWND, but there are CWND number of acknowledgements, so it amounts to adding the window size by 1. And now next time when you send, you can send 1, 2, 3, 4, 5 because you slide the window by 5, and one more because you increase the window size by 1. Okay, and this keeps on going. So you've got 6 packets, and then assuming that there's no congestion and therefore, at least for wireline network, there's no loss, you go to 7 after another round-trip time, and then go to 8. So as you can see, this is a linear additive increase in order to try to get the most efficient usage of the network capacity. But it turns out at this point, together with the actions of transmitting packets from the other sources, congestion is induced somewhere in the network along the path used by this particular source. And how do you know that? Well, you may know that by timeout timer, you may know that by 3 duplicate acknowledgement. And therefore you say, whoops, there's a loss, or at least I infer there's a loss somewhere in the network, and that implies in turn that there is congestion. All right, I'm going to therefore penalize myself in a multiplicative way. Okay, try to avoid congestion now by reducing the transmission rate by reducing the congestion window size, CWND, cutting 8 in half down to 4, and now this keeps on going again. On the other hand, if it is a delay-based congestion inference, for example, in FAST or in TCP Vegas, then the story is a little different. Now, first, we have to decompose the overall end-to-end delay into 4 components. Okay, a propagation delay, queuing delay, transmission delay, and processing delay. Now, propagation delay is due to the fact that you have to traverse a physical distance and you can't be faster than the speed of light. Queuing delay is what we are most interested in here because they refer to the time you spend waiting inside a router for the egress link to be available on the output port, as we saw in the last lecture on routing. So this is congestion induced. If there's no congestion, then the egress link on the output port is always available. There is no queuing delay. But as congestion gets heavier and heavier, queuing delay also will go up. Then there's the transmission delay, because a packet is of finite size, so starting from transmitting the first bit to the last bit takes some time. Finally, there's processing delay. For example, looking up at the forwarding table. Usually, we say the transmission and processing delay are relatively insignificant compared to a long-distance propagation delay and the possibility of congestion-induced queuing delay. So if we look at these 2 main components in a normal situation, you see that when congestion is very light, you're basically looking at round-trip time being the propagation delay. As congestion goes up, your total round-trip time or delay goes up. So if you are looking at the transmission rate, assuming there's a minimum queuing delay with almost no congestion at all, then you are talking about the transmission rate X being CWND over RTT min. Okay, smallest RTT that you have experienced in recent past. But if you are looking at the transmission rate X when there are some levels of congestion, then it equals the congestion window over the current RTT. So RTT mean is some constant. You have estimated RTT. This one is the current at time t. Okay. To be more precise, you have to multiply by the average packet size measured in bits. Okay. But if you measure it by packets per second, then you can just compare this with this. And what happens is that you would say, let me look at the difference between the transmission rate with a minimum queuing delay versus the actual transmission rate I'm currently getting. Okay. And if this difference is very big, okay, then that gives me some information about the current congestion condition. Okay. For example, if this difference is very big, that means that this round-trip time at this point is very big. Okay. And therefore, this number is small, and therefore the difference between these 2 numbers is big. So if this difference between this ratio and this ratio is bigger than the threshold, okay, for example, threshold is 3 units, then that means there's some congestion, and I'm going to reduce the congestion window. So let's look at this difference. If it's bigger than some threshold beta, that implies CWND should be reduced, say by 1 unit. On the other hand, if this difference is smaller than a threshold, let's say the same threshold, then that means CWND can go up, because if it is smaller than a threshold, it means that this current round-trip time is not too much bigger than the minimum round-trip time. Now, what about if the difference is exactly equal to this threshold beta? Then you say, well, this beta is basically telling you how many packets you can tolerate to be in the flight between the source and the destination. Okay, and you say, all right, then I can tolerate this many packets in transit from the source and destination, and the congestion window size would remain the same, CWND, no change. Okay, you don't increase it by 1, you don't decrease it by 1. So when all the sources have their difference between these two ratios equal to beta, then there's no one that's changing, and that reaches an equilibrium. We haven't touched upon equilibrium concepts in a while. We talked about game-theoretic equilibrium in strategic thinking. We talked about equilibrium in a fixed point equation, and this is the equilibrium for an iterative procedure, like this congestion control protocol. Okay. So if we compare between these two different philosophies, this is loss-based, this is delay-based. Typical chart you will see of congestion window over time t. For loss-based, it will linearly increase, then it will have a sharp drop, multiplicative decrease, linearly increase, sharp drop. So you see the zigzags going on. Whereas for delay-based, because you're using an early and continuous signal instead of a late and binary congestion signal, you might hope for the convergence of this oscillation through some kind of damping and eventually converge with very little ups and downs around a desirable equilibrium. And that will be the target. The target is to say that distributively, I want to find out what kind of capacity I should allocate to this particular source. I do not have a bird's eye view, but maybe through some implicit message passing, like the timing and the presence of packets, I will be able to determine the right one. For example, the right level is this. Okay, this is your optimal congestion window size. And this is a way to distributively, locally search for that, just like small world, algorithmic small world, where greedy routing may be able to search distributively for a short path between source and destination. So now our question is, can we indeed find a distributed solution to do capacity allocation?